DuckDB under the hood, Module 7. Same predicate, 2 columns, but a 10 times difference in query time. The query where TC1 equals 500,000 takes 1 millisecond, touching only one row group out of 814. But the query where TC2 equals 500,000 takes 10 milliseconds, touching all 814 row groups. Same table, same 100 million rows, same value. DuckDB reads column statistics before touching any data. DuckDB under the hood, Module 7. DuckDB stores each column in contiguous chunks called row groups. Each row group holds up to 120,000 rows. For example, 100 million rows results in 814 row groups with 120,000 rows each. For every row group, DuckDB records the minimum and maximum value per column. These minimum and maximum entries are called zonemaps, and they are automatic, so no create index is needed. Ordering determines how useful zonemaps are. If you have an ordered column C1, its values increase monotonically with storage order. Row group spans are narrow, such as 0 to 122,000, then 123,000 to 246,000. A predicate on C1 equal to 500,000 matches exactly one span and skips 813 of 814 row groups. But if you have a random column C2, values are uniformly scattered across 0 to 100 million. Every row group spans nearly the full domain, so the skip count is 0. DuckDB exposes raw storage metadata through a built-in table function. You can query the pragma storage info table function, as shown here. The stats column shows the minimum and maximum values for each row group. Here, the minimum is 0, the maximum is 122,876, and nulls are not present. From this, you can compute the span per row group and count skippable groups. There is no special tooling required, just standard SQL against any DuckDB table. After an update, DuckDB does not rewrite the zone map immediately. Affected row groups are flagged with has updates equal to true. New minimum and maximum values are tracked in separate update statistics storage, tagged with transaction information. There is a scan overhead to fetch extra stats for each flagged row group at query time. A checkpoint or copy to a new file merges the updates and removes the flag. First, create a table T with two big columns, C1 and C2. Next, insert 100 million rows into T. The C1 column gets values from a sequence, bitwise ANDed with a mask. The C2 column gets values derived from a large integer calculation, modulo 100 million. The explained plan for the ordered column C1 shows a table scan with filter C1 equals 500,000. DuckDB finds the matching rows nearly instantly. The zone map for the ordered column eliminates 813 of 814 row groups before any data is read. Only the one row group whose span includes 500,000 is scanned. The same query on column C2 is 10 times slower. The plan is identical. Table scan, same filter, same matching rows, but every row group has a zone map spanning the full value range, so none can be skipped. All 814 row groups must be read before DuckDB can return the result. This output shows the internal storage of the table T. Each row is one row group for one column. It shows the row group ID, the column name, and the statistics. The statistics field contains the minimum value, the maximum value, and a flag for whether nulls are present. Here the minimum is 0, the maximum is 122,876, and nulls are not present. First, create a macro called ZoneMap that returns the minimum and maximum values of a column. Now check how many rows can be skipped using the zone maps for column C1. The query returns the count of rows where 500,000 is not between the minimum and maximum values. Repeat this for column C2. This shows how zone maps can be used to skip reading unnecessary data. After an update, DuckDB marks affected row groups with has updates equal to true. The zone map rewrite is deferred until checkpoint. Let's run this against table T now. Here, we update the table T setting C1 to its negative value. This flips the sign of all values in the C1 column. Next, we query pragma storage info for table T. We filter for big int segment types. We limit the output to the first 10 rows. The has updates column will now show true for the updated segments. Here's an exercise for you. Predict the skip count. First, create table T with column 1 ordered and column 2 random with 100 million rows. Question 1. Which predicate skips more row groups? Column 1 equals 500,000 or column 2 equals 500,000. Question 2. What does the explain analyze command show for rows scanned in each case? Question 3. after update tset column 1 equals negative column 1, which storage flag appears? You can find the answer in 04 exercise MD. Welcome back. Let us walk through the exercise together. We create a fresh table saw with 1 million rows. Column C1 is ordered using the same bitwise AND formula as the walkthrough. Column C2 is random, spread uniformly across the value range. Question 1 and 2. Which column skips row groups? For the ordered column C1, Zonemaps spans are narrow. The explained plan confirms only the row groups whose span includes 500,000 are scanned. At 1 million rows, there are roughly 8 row groups total. All but 1 are skipped. For the random column C2, every row group spans the full value range. No row group can be ruled out, so all 8 are scanned. At 1 million rows, absolute timing is too small to compare reliably. The skip count is what matters. 0 row groups skipped for C2 versus 7 for C1. This confirms ordering determines skip effectiveness. Question 3. After the update, which flag appears? We negate all C1 values and then query pragma storage info. The has updates column is true for every C1 row group. DuckDB defers the zone map rewrite until checkpoint. Let's recap what we covered in this module. Row groups hold up to 120,000 rows, and there is one zone map containing the minimum and maximum per column per group. Ordered columns with narrow spans allow most row groups to be skippable. Random columns with full domain spans result in 0 row groups skipped. The pragma storage info function exposes raw zone maps from SQL. Update marks has updates, which adds a slight overhead at scan time until checkpoint. Next up, Module 08 ART indexes.